Then we said the, and we also mentioned here for the signal that signal would be having a bandwidth. So any signal would be having a bandwidth, and we will call that bandwidth of the signal WS. Then you said signal has its own bandwidth, but medium will have its own bandwidth. And oops, let's say messed up this medium too much. And we started calling this medium channel. And we said channel has its own bandwidth. Then we said when you have channel bandwidth, you cannot use all of the channel bandwidth. It will be reduced to C, capacity. And we learned that through Shannon equation. Why it would be reduced? Due to noise. What we get the noise notice from signal to noise ratio. And signal to noise ratio, if it increases, what it will do, it will start flipping the bits. So my signal becomes weaker, my noise becomes stronger. So bit which is in digital communication plus would become negative, negative will become, will start flipping. And that would introduce bit error rate. Depends how many bits are being flipped over. Then in this context, we related all of these arguments. We said, okay, WC, C, R, SNR, bit error rate, they have a context in this discussion. And we said that always R is less than capacity. So I should use these signs. R should be less than C, right? Because you cannot reach the capacity because R is always less, as we discussed. So now this is all sort of things which are related to medium. We also said medium would have effect on the signal. Signal we discussed earlier. What kind of effect? It would act as a filter. Medium would act as a filter. One example we took was low pass filter. Okay, so when we were discussing signal, when we discussed analog and digital, then that was also mentioned that signals different frequencies. So various frequencies, they undergo a different amount of attenuation and distortion. We also talked about this, right? So then we said as a signal goes different amount of attenuation and distortion, then it has, the medium would have an impact like a filter, for example, low pass filter. And then we said low pass filter would be, in an ideal case, would be sort of this. And in a non-ideal case, will be sort of, oops, I pressed the button, will be this. So this is ideal. and this one is non-ideal. I say if this is the frequency and this is the amplitude, so as the frequency increases, you can see the amplitude will decrease more. Right? So if you compare the amplitude here, amplitude here, amplitude here, so you see they all are different. They should be same. They should be same as the height of the okay. It should be same as the height of this is, because this is not ideal. This is non-ideal practical. So various um, frequency component would undergo various amount of attenuation, different amount of attenuation. So that's where attenuation comes into picture. And as far as distortion comes, then we say, then you will be looking at as the frequency goes, then you have a phase, and ideal phase is like this. This is ideal. That's how the phase varies. But in a non-ideal situation, the phase will vary like this. So it means with the increase in frequency, if I increase the frequency, the amount of phase which is being varied will be all different as shown by these red lines. So here it is different, here it is different, here it is different, here it is different. And they are not following sort of a straight line, so they are following a curved line. So that shows that the amount would not be changed. So it will be changed a different ratio as it was with the blue line. So we said, oh, the medium would impact the signal and like this. So once we hit this, then we said, okay, as we have learned from here, that's how a waveform should be analyzed and that's how the waveform is constructed. Then we started moving in the third quadrant, and that's where we went to Fourier transform.